Well, thanks a lot for the nice introduction. I'm not really sure if my talk should be called Dive into GPGPU Programming, because I'll be talking about different libraries and systems that you can actually use to build like large GPGPU-oriented systems. But before we start, there's a slight chance that my nose will start bleeding during the presentation, so don't be afraid. And like if you like gambling as much as I do, we can make a bet. I estimate the chances to be about 20%. So I accept 1 to 4 bets. So a couple of words about myself. I'm 24 right now. I've started programming in about elementary school. I started with web programming. I went to mobile development, desktop programming. Then for a few years, I've been studying astrophysics, and I was doing scientific computing for simulation purposes. And for the past 4 years, I've been involved into high-performance computing framework design. So I'm more or less related to GPGPU for almost 10 years now, about 9 years now. So this talk is not like an introduction into like what's GPGPU or what is a GPU. I expect all of you to more or less understand the hardware differences between the CPU and the GPU. This talk will be primarily for guys who do a lot of number crunching, like AI, data science, video processing, and everything related to this. And the reason we do this, why we select GPUs for number crunching, is that sometimes we can get enormous performance increases. So this slide was taken from NVIDIA website. They've compared the performance of linear algebra operations implemented in BLAS libraries designed for their GPUs and for CPUs, and they claim 35x performance improvements in one versus the other. And why GPUs are primarily used for the stuff that I do, just because they allow us to do lots of simulations and lots of number crunching at the same time. So this thing, it's not just physics simulation. This is AI learning how to control all those bodies. So there are 2 videos on the screen. The left one was generated using the classical physics simulations. It does about 3 frames per second. The right one was generated using a neural network. It does 3,000 frames per second. So it's 3 orders of magnitude performance improvement using neural networks as approximators for nonlinear mathematics in everyday physics. And this translates into like enormous models. So this specific model, 3D model, does 114 frames per second. And it manages and computes 640,000 vertices in real time. 640,000 vertices. So just shy of a million. Okay, back to our primary topic. We as developers, we generally just want the same things, and it's invariant of the problem set. We want to write our software just once. We want to deploy it on every kind of device, every kind of platform. We want to optimize it for performance just because we are C++ programmers, and we want to avoid boilerplate. So we want our code to be concise, simple, nice, and efficient. Generally, it means the following things. So we want to have all our code, no matter if it's a GPU-oriented code or CPU-oriented code, just stored in one single binary file. And before that, we want it in a single source file, so in a CPP file normally. We want to deploy it on FPGAs, on Intel hardware, on NVIDIA hardware. But this requires, oh, just sorry, like, can you hear me? Is it okay? Okay, thanks. So all those nice, beautiful things, the cross-platform deployment and simple code, they generally require a lot of stuff. They require a unified language for abstractions, both on CPU side and the GPU side. We want compilers that are modular enough so we can add backends every time we want to deploy our models on a new kind of accelerator, an ASIC or a GPU. We want to write our software, and we want the compilers to actually tune everything related to deployment without actually changing our logic. So this is a broad set of problems, and it's totally impossible to cover all the potential use cases in just 1 hour talk. So our aim for today is actually to fill this simple table. So it has just 4 columns. I'm going to maybe suggest 4 different recipes depending on your use case, so that once you start designing your GPU systems, you can select the one that works better for you. One of these solutions will be super simple. It will require maybe just like 20 or like 10 lines of code to start, and you'll already be able to do some linear algebra, neural networks, or something else. But some of the later versions, like the flexible and unified solutions, will be much more complex. But don't worry, we have a plan. So we'll first start with covering the classical languages that exist in the GPGPU world. We'll cover the actual patterns in writing this software in the bare metal style, so like right next to the device itself. And then we'll go a bit higher level. We'll look into different systems, different libraries, and maybe even compiler toolchains if we have enough time to see if we have to do everything on our own manually or we can use higher level tools. And to start, let's talk about the communication. So those are two separate devices, the accelerator, the GPU, and the CPU. They have different instruction sets, so we basically need some kind of an API to talk between those two and synchronize. The earliest one of those was proposed by a company called Silicon Graphics, and the company and the standard itself is actually older than me. It was started in 1992, and in 2009, the company went bankrupt. But don't worry, because OpenGL as a standard is maintained by a large Kronos group, so it's still maintained. I wouldn't say it's evolving. And it's still supported on almost all platforms. And Apple ecosystem is notoriously well known for like deprecating support for all the major APIs, including OpenGL. So they dropped OpenGL support in iOS 12 a year ago. The first actual GPGPU platform to appear, not a graphics platform, was CUDA. It's an amazing ecosystem. It's very broad. It's very powerful, but it has one serious downside. It's only deployable on NVIDIA hardware. So now we'll go from like the least deployable, the least cross-platform solution to the most cross-platform solution, which is OpenCL. It was designed by Apple in 2009, but since then they've done very little to support the standard itself. They kind of deprecated it. They don't support it on iOS. There's a limited support on macOS for older versions, but almost everywhere else it's supported. So this chart is exceptionally outdated for our tech industry. It's dated 2015, but it shows that at least older versions of OpenCL, the 1.2, is supported on almost all kinds of platforms. And what's amazing is that you can see Xilinx on the left side. Xilinx is a company that manufactures and designs FPGAs. They are not designing GPUs. So basically, they work on compilers that are able to transform our OpenCL code into a hardware describing language, like a Verilog or a VHDL, and basically redesign the structure of an FPGA for our specific problem solved using the OpenCL ecosystem. The next platform that appeared was Metal. It was also designed by Apple, so they deprecated the OpenCL support, and now their Metal version is actually closer to C++. OpenCL is a very outdated system. It's primarily based on C, and there is not much progress in the compiler division. So probably the last but not the least, the most powerful standard of all is Vulkan. It was proposed by AMD. It's supported everywhere. It's primarily graphics-oriented API. But as it's so flexible, you can use it for almost anything, including compute. So all of those APIs, they're very different. They have different base languages. Two of them are based on C++. Primarily, they are based on C. Vulkan is kind of unique because it actually doesn't require a specific language for the input. You can actually design your software for Vulkan in any language and then generate binaries, and they're basically like a bytecode, so you can deploy them on almost every kind of architecture of GPUs. So it's a very broad topic. We'll just focus on CUDA and OpenCL, maybe Vulkan in the very end. And let's compare CUDA and OpenCL. So those two things are pretty famous. Are they different? I claim that not that much. So like the shared common denominator of those two platforms is actually very similar. But before we start, how many of you have tried writing GPU code before? Can you raise hands? Okay, still half of the class has never tried it. So we'll probably stop over here for a second. So the top line is a function definition for a CPU. So it sums up two numbers. It takes two pointers to memory buffers that are input buffers, and then also a pointer to output buffer, and also the length of the input arrays. They all have same lengths. So we have to sum element-wise the two arrays and output the sums into the last array. The same function will look differently depending on if it's designed for a CPU or for GPU. So they have a different number of arguments. In the GPU version, which is below, we often don't pass the length of the array because it's implicitly defined on the CPU side, not on the GPU side, because we define the shape of the computation and we select the name of the kernel that we want to run on the CPU, and then we pass it to the GPU. And then the GPU should be able to internally understand which part of the computation it's responsible for and what's the actual size of the entire computation. So as we see, the languages for CPU programming and GPU programming are somewhat different. And we require some keywords that will make life easier on the GPU and parallel computing side. So the two obvious things that come to mind are synchronization primitives, basically letting every single thread. And on the GPU, we have like thousands of threads. So we want every single thread to understand its specific role in our computation. So every specific thread receives some kind of identifier, and it uses this identifier to understand which part of the computation it's responsible for. The second important part, probably even more important one, is the memory qualifiers part. So when we do parallel programming, we try to avoid memory races and everything related to it. In languages designed specifically for this, we actually have keywords that limit the access to a specific memory buffer. So for every time we define a pointer, we have to provide an additional keyword, a qualifier that says if it's a global memory buffer, a local memory buffer, a constant memory buffer, or a private memory buffer. And as you can see, there's basically a one-to-one mapping between every category of memory qualifiers in OpenCL and CUDA ecosystem. The only caveat is that the local keyword in OpenCL means the same thing as the shared keyword in the CUDA ecosystem. So there is this tiny source of ambiguity, but you get used to it. So one thing that you can note is that OpenGL, which is a graphics API, targets the same devices as OpenCL. They both target GPUs. And physically, the devices are the same. But from the logic perspective, we want different keywords and different abstractions layers depending on the application. So the keywords that we use for memory qualifiers in OpenCL and CUDA are very different from the ones that we use in OpenGL. And the logical memory types that we just discussed are different from the actual memory types that are presented over here on this slide. So they all have very different number of compute units. They have different sizes of constant buffers. They have different sizes of local memory buffers that are designed physically on the chip. To make things worse, actually, like NVIDIA and AMD, they don't have some kind of standardized approach in terms of what's the size and the number of constant memory buffers designed in silicon. So NVIDIA GPUs generally have just one single constant buffer, and then allocate everything else that's called constant memory just on a heap. And with AMD's, it's even more tricky than that. They have a fixed size of a constant memory buffer, 64 kilobytes, but you can have many constant buffers on the same device that are disconnected from each other. And then everything that is beyond 64 kilobytes will also be allocated in the global memory heap, even though you call it a constant memory. So every time we define a pointer, as I told you, we have to provide this additional keyword like a global, which states that the memory that we are pointing to with this pointer is actually located on the heap. Other than that, the terminology differs only in terms of the size and the grouping of the threads. So when we have so many threads, we want to organize them in some kind of hierarchy. If we just have like a flat company structure, it's very hard to scale beyond, let's say, 800 people in everyday businesses. In GPU computing, it's more or less the same. If you have thousands of threads, if they are not synchronized or grouped with each other, it's very complicated to write interesting, powerful programs. So basically, groups of threads are called blocks in CUDA, and they're called rock groups in OpenCL. Other than that, it's more or less the same. And the last, but probably not the least, maybe the least, is actually the way we index the actual threads. These are not function calls, even though on the OpenCL side they look like function calls. Those are actually keywords included into the language that you can use to query the device and the environment about the specific role of this current computation, like in the entire program. For memory synchronization, there are some differences. So on the OpenCL side, there are a couple of synchronization primitives like read mem fence and write mem fence. But to be honest, I've been doing GPGPU for about like 9-10 years now. I've never seen anybody using them. Like I've actually scanned GitHub. I've searched through the entire code base with this specific keywords, and nobody is using them. So you can just limit yourself to the first row. And if you're doing GPGPU programming, in maybe like 99% of cases, you just need sync threads or barrier in the OpenCL world. So we've already talked about those two parts. They are not really interesting. They're kind of boring, but you have to know them. There's the third part, which actually changes everything from my perspective. So, but before we get to them, let's cover some bare metal examples. So the tasks that we primarily optimize for GPUs are the data parallel tasks. It's a very simple definition. You just have the number of outputs that's proportional or generally equal to the size of the input object. So if we have like 1,000 numbers as an input array, we produce another 1,000 numbers as an output. And basically, you can inject all kinds of functions. You can do element-wise operations. These kind of operations are just designed to be optimized on a CPU, on a GPU. It's like the bread and butter of GPUs. So this is how we designed the C code to sum up two arrays of numbers element-wise. I don't think it's new to anybody. This is how it looks on OpenCL. So we remove the explicit for loop. As you can see, we have a for loop over here. We don't have it on the OpenCL version. We just have this I index, which is used to query the environment for our actual role in the computation. So just for reference, this is how GLSL looks. This is a shader language. Sometimes people use it for GPGPU computations like 10, 15 years ago, before OpenCL was a thing. But right now, it's more like a remnant of a past, and almost nobody uses it for computations. The tricky things come up when we start working with concurrent problems. So let's say you have an array of numbers, and you want to reduce the entire array to the sum of numbers in that array. So you just want to sum up all the numbers in one single array. In serial code, it's super simple. In the GPU-oriented codes, it's very tricky, because you cannot write into the same variable from 1,000 threads. So like if you split your 1,000 numbers between 1,000 threads, every single one of them will be trying to access the same output variable and sum up everything into one place. Generally, to avoid this, people split and developers split the operation into multiple iterations. So you make batches of threads or batches or subarrays basically, and every thread is responsible for summing up, let's say, 10 numbers, and then it's called recursively in the second iteration to sum up the smaller array. Sounds simple, not that easy to implement. So on the GitHub page related to this talk, you can find some of the implementations for OpenCL CUDA, Vulkan, and even Metal, the Apple's GPGPU language, or dialect, if you will. So if you want to sum up all the numbers in an array in OpenCL, this is the simplest version that you can make. And I have 6 versions of this program, differing only in the way that you put locks and memory barriers and synchronization primitives, but the logic is exactly the same everywhere. You can actually benchmark and compare 6 implementations on your different machines. The numbers will vary a lot depending on the size of the batch, the size of the original array, and the specifics of your machine. And OpenCL can be deployed not just on the GPUs, but also on the CPUs and FPGAs. Depending on that, the numbers will be different. In my case, the difference between the slowest implementation and the fastest implementations was about 1 order of magnitude. So basically, depending on the way you put this one of those memory barrier lines, the difference can be as drastic as using, let's say, 10 servers and 1 server for doing basically the same work. So this is how the second version looks like. It has one of the loops unrolled, but other than that, it's the same 2 memory barriers that we have. Very complicated, right? So we want to move into the higher layers, so we can use simpler tools to design our software much faster. first thing to start with is the linear algebra libraries. Probably many of you have heard about BLAS and LAPACK. How many of you have ever tried BLAS or LAPACK in their applications? Can you raise hands? About a dozen. So you probably already know that BLAS is like a more low-level library that kind of implements only the vector-to-vector or matrix-to-matrix operations. Generally, BLAS and LAPACK are not just libraries, they are APIs, and every vendor designs its own implementation for this specific API. The implementations vary in terms of the number of supported types, which is, for example, relevant for my specific industry, AI. In AI, a bunch of operations has a very low performance, very low accuracy requirements. So we actually want floating point 16 instead of floating point 32. And QBLAS, which is the CUDA implementation of the BLAS library, provides this. Many of them do not. LAPACK is a more high-level library. It uses BLAS as, very often it uses BLAS as it's one of its internal components. And they're actually huge. BLAS has 152 operations defined in its API. It takes time to implement all of those. But generally, what you expect from them is like something like a vector sum or array reduction, right? But not quite that much. So the problem is many of the operations that we think are logical are not part of the classical linear algebra routines. So they were not included into the BLAS API itself. So if you want to just sum two arrays element-wise, you cannot do directly. You cannot do it directly with a BLAS. You can bypass it using the SyCL array, or like you can reduce the number of values in an array to their sum with S dot. But you always have to store some kind of array of ones, like a unit, an array, a vector of length 1, to basically perform all those kinds of operations. And another problem is that once you use those libraries for accelerated mathematics, or linear algebra, if you will, you have those super advanced, very optimized implementations for every specific piece of hardware. But once you compose them together, you end up with slow pipelines. Having fast kernels does not always translate into fast pipelines. We'll later discuss why it's the case, but getting back to the picture that we had in like the very beginning with the NVIDIA on it, with the QBLAS implementation, they actually compared two very different types of hardware, so I wouldn't trust their numbers quite that much. So they claim 35x performance improvement when comparing a 2017 V100 GPU, which is on the right on the table, and the E5 Xeon CPU, which is on the left. So the GPU is 4 times more expensive. It's a year younger than the CPU, and they have basically very different purposes. So especially older CPUs, they had a huge set of ALUs that are specifically designed for integer operations. Nowadays, our CPUs kind of converge with the GPUs, and the column in the middle, which is like the gold Xeon CPU, it has a ton of various ALUs for floating point operations, so it's much closer to modern day GPUs, both in terms of performance and actually in terms of price as well. The next layer of abstraction beyond like the language, which is like bare metal, and then the linear algebra libraries is the lazy evaluation graphs, if you will. So like it's really hard to find a name that will fit all of those titles, but I think they're kind of similar. They're primarily libraries that do mathematics, and depending on the library, they do it in a different way. So Eigen is a pretty well-known linear algebra library. It uses templates to pass operations. So basically, you have two matrices. If you multiply one by another, you are not getting a matrix. You're getting a template of an expression that encompasses the first matrix type, the second matrix type, and the kind of kernel that you want to apply to it. So it's fully compile time. It's super fast, but only if you run it on the CPU. Their GPU support is very limited. So if you want to do GPGPU and have more or less the same functionality as Eigen provides, you actually have a quite broad range of functionality. And I suggest everybody remember the titles of those libraries that I have on top: Arrayfire, Boost, Compute, and Thrust, and VexCL. They do more or less the same. They are very similar. Primarily, they do just-in-time compilation. They are not statically typed, so you have code that looks somewhat like Python code, which is a bad thing from my perspective. But on the opposite side, it's very easy to maintain. And it uses just-in-time compilation to actually compress all those kernels applied separately into one continuous sequence of operations applied one after another. And probably the best metric to use when selecting a project like this, especially at the early stages, is the number of stars on GitHub, because you want support. You want to be able to learn something from the environment, especially if it's like your first project. So we had the data parallel task, which are super easy to implement on GPUs. Can we make them actually even better with those higher level tools? Because like the code itself is quite simple, but actually it doesn't stop there. So one of the things that I like to do is getting back to physics, because like the nature defines everything, all kinds of limitations. And the primary constraint that we have nowadays is the cost of operations from the power perspective. So cost of summing up two numbers on ALU is basically 1 picojoule. Just saving number to DRAM or querying DRAM to get this number is 1,000 times more expensive. So it's kind of obvious that we need something more than inlining, or we need it for kind of data-oriented purposes, not just passing functions here and there. So that's called kernel fusion. From my perspective, it's like the next natural step after inlining. And there are actually quite a few systems that do kernel fusion quite well. So basically, kernel fusion means that you have a set of operations. You have the kernel number 1, the kernel number 2, and the kernel number 3. So instead of taking the entire array, putting it onto the GPU, computing the first kernel, and then outputting it back into the memory, then doing the same over and over again for three operations, one after another, you actually chain and fuse all 3 operations into one single function. So every time you load something into the registers of a GPU, you can apply 3 operations one after another if they're data parallel, and you reduce the costs by a wide margin. So the final program will become probably 2-3 times faster than the original one. And some of the systems that implement this are actually beautiful and make us learn something new about programming in general and control flow. One of them is Halide. I like it a lot because it separates the inner logic of the operation from the actual structure of the for loop. And it's actually used in many modern companies, and like some of the largest companies on the planet that do image processing use Halide to accelerate all of the image analytics that they have. So this one looks super simple, right? We have a function that is defined, that is parameterized over I. Looks like a higher level language, right? And we take element at index I from array LA and array LB, and we sum up those 2 values and we output it into the function itself. But there is a little more boilerplate code, because this is not just a language. This is an embedded language. This is basically a C++ library that is designed with LLVM as its dependency. So the binaries of the library is around 80 megabytes. So you should probably be cautious about like embedding it into your product. But it provides some amazing capabilities. So the boilerplate code here starts with the Halide namespace. We define 2 buffers. We design a variable that we predefine called I, and then we define a function. And then all we do is define the actual logic of a function. What goes afterwards is we call a realize function. A realize function lazily calls this original function with a specific size of an input. So xlen, which is the length of the input, is passed as an argument into the function afterwards. And what Halide does, it generates the for loops for you. Sounds simple, right? But not that much. And well, I would say it's simple, but the beauty is that it's very powerful. So you have this original realize function. You can replace it with a parallel function. With just 6 or 7 new letters, you replace your serial code with parallel code. And you can go beyond this point. So you can vectorize your original for loop. What we often do in high performance computing is, instead of having a for loop array that goes, let's say, from 0 to 64, we'll instead have a for loop that goes from 0 to 8. And inside of the for loop function, for loop body will unroll the for loop. So we'll basically vectorize it in a way. But this specific vectorize keyword or like a function call, it actually does more than that. It uses SIMD instructions if they are available on the platform. It automatically generates code as if our type of the input was not a floating point number, but a SIMD type float 8, which is a fixed length array of floating point numbers concatenated one after another. And we can go beyond that. We can do actual array or for loop unrolling. For that, we can actually split our original variable I, which is the primary argument of the function call, into two different indexes, the j index and the k index. And instead of making like a for loop over I, we're having a for loop over j. And inside of it, we're making a loop unrolling with a variable called k, which is internally vectorized with SIMD instructions. So I'm changing the shape of the function dramatically with just a couple of function calls. And what it does is basically eliminates the primary bottleneck that we have in the industry, which is the fact that we spend a lot of time working and optimizing on high performance code instead of actually designing the logic of our computation or designing new algorithms. So one of the common examples in the image processing is a blurring filter. And we all know that depending on the data locality and the way you traverse the two-dimensional structure, you will have a very different performance result. In one case, if you're storing your data row by row and you're traversing it column by column, you will have high performance. But very often you need to do both. So when you do blurring, you basically combine the pixels horizontally and then vertically. So you may want to optimize this. And here are two different implementations. One of them is on the left side, it's Halide. It's very simple to look at and to reason. The one on the right is C++ implementation for SIMD instructions. It's just for one platform, so it's platform dependent. The performance is the same in both examples. But in the first case, in Halide, you can actually deploy the same code and generate binaries for every kind of GPU, both for NVIDIA architectures and for AMD architectures, for AMD devices. You can generate SIMD code for Intel devices, or like do whatever you want from this point. You can do meta-programming, analyze the structure of your computation, generate intermediate representations. And I have one more example that probably will make you love this system. It was actually designed in MIT in 2013, but since then it received so much admiration that it's becoming like an industry standard. So there was like a case study. There was like a big image processing company. It's basically a legend, so I don't want to say any specific names. But there was like some kind of a reference representation for, or reference implementations for a Laplacian filter, which is another common technique used in image processing. It was like 300 lines of code. No one knows how much time it took to write it. It was probably quite simple. But then if we take the performance metrics for this specific implementation as 1x, we can later compare it. Oh, I have the name of the company here. Okay, so this company designed an optimized implementation. It took about 3 months of a senior developer's work to design an implementation that was 10 times faster. The volume of the final code was 7 times larger than the original. Oh, no, 5 times larger than the original. Can it be better than that? Well, it can be better with Halide or Halide. So the final representation, the final result for Halide was 60 lines of code. So it's 5 times smaller than the original one. It took 1 day of a junior intern instead of 3 months of a senior developer's work to design the implementation for Halide. And then the result was 20 times faster than the original and 2 times faster than the fast SIMD-oriented implementation that was designed in Adobe. And the best part of all, like this is just the beginning, it works everywhere. So you have the same code, you produce binaries, LLVM does all the magic internally. So you get the original CPU implementation, which is 20 times faster than the original, and a GPU implementation that is 70 times faster than the original. Quite nice, right? And just with 60 lines of code and 1 day of work. This is efficiency, this is productivity. So We had a discussion yesterday about Go versus C++, and like if you need garbage collection in modern day computing. I'm very much pro high performance computing, but when you can merge high performance computing with actual ease of use, you get amazing tools that will basically push you forward many, many years ahead, and you will bypass all the competition on the market. So it's relevant to know. Another system that is more like a prototype nowadays, but has quite an impressive potential is called SyCL, SyCL. So the CL suffix kind of reminds us of OpenCL. And there is a good reason for this. So basically the SyCL standard builds upon the OpenCL standard that was before. It's maintained by the same Kronos group. And this is the first actual way we can get real heterogeneous computing in C++. So this looks like C++ just because it is C++. So imagine writing your general C++ computing routines and using STL algorithms or something like them, or using lambdas in the same source file as you do as the one that you use for logic or database accesses or graphics or whatever. With this specific system, you will be able to write your lambdas in a very natural way like we do in C++ that will do the same. But there is one thing that I hate about this slide. Actually two, but we'll cover the second one later. It's the huge amount of boilerplate that we have. So the meaningful line is somewhere in the bottom. It does a very simple thing. But to get to this point, we had to write 4, 8 lines, or maybe like even 10 lines of boilerplate. And it's very easy to mess up. But as we get ranges in C++20, we can maybe transform our original code into something that looks like this. So as we get executors in C++23, we will be able to pass execution policies or like the executor itself as the first argument into like the STL algorithm. The same way we may be able to pass SyCL policy, which is basically a policy that determines the way you select a GPU for a specific lambda expression or a specific workload. And it's also responsible for actually managing the lifetime of a computation and synchronizing it with the rest. It sounds very beautiful, especially with the spans and ranges and operators like std+, but it's very complicated. So it's not just some kind of a plugin or a library that you can use. But I do not obviously expect you to read through this slide. It's very complicated even for me after like years of doing this stuff. Here are like the bullet points, what you should know. It's not a language, it's not a library, it's not a compiler. It's a combination of a library and a compiler. So the obvious outcome like that you can think of is that to support SyCL, you don't only need a modern library, you also need a compiler support. So every time you want to compile something written with SyCL, you need your compiler to actually have extensions for GPGPU computations. And the way it works is that you have this powerful compiler that basically separates your original code base into two parts. One is just the CPU-oriented code, the other one will produce GPU kernels. The SyCL device compiler will try to generate a special binary that is called SPIRE-V. This is the type of binary that is used as an input into the Vulkan API and to most modern GPUs. You can actually deploy it almost everywhere. It kind of reminds us of the stuff that we already have within the NVIDIA toolkit, namely the QBean and PTX. But the difference is that QBean is like the intermediate representation that you have for NVIDIA hardware, but only for a specific set of architectures. So between the architectures, let's say Pascal and Volta, which are the two generations of graphics card by NVIDIA, the QBean for the same algorithm or for the same implementation may be very different. Furthermore, there's also like another representation which is called PTX in NVIDIA. And as I told you, NVIDIA is like a very closed ecosystem, so you cannot use PTX for AMD GPUs. With SPIRE-V, you will be able to deploy them on AMD, Intel, and NVIDIA hardware as well. So it's a huge mess at this point. That's why it's kind of hard for me to recommend it. It's only one of the recipes that I'm going to show at the end. So right now, LLVM is already huge, and everything that's currently being built around the GPGPU is very often built around the LLVM toolchain which is kind of reasonable, but it's hard to reason about, and it's hard to go through this entire code base because LLVM is 95,000 lines of, actually 95,000 of files, and it's about 5.5 million lines of C and C++ code. So we had this kernel fusion thing. When we combined multiple computations together into one continuous sequence to produce faster binaries that actually save time and keep the data in the GPU registers for as long as possible. Those numbers were not measured by myself, but I kind of trust them because they remind me of my performance gains that I had like a few years ago when I started doing kernel fusion more extensively. And the numbers here basically show off the OpenCV, which is the image processing library, a very well-known one, Halide in the middle, and SyCL. And as we can see, SyCL being more integrated into the LLVM toolchain produces the fastest executables. So the final part, probably. The 4 recipes that I've promised start with the unified solution, which is kind of complicated. If you want to be as cross-platform as possible, I would probably suggest writing OpenCL code and then generating SPIRV binaries and then building some kind of a Vulkan system for asynchronous computing and then passing your binaries into the Vulkan computational graph and basically building all the semaphores and callbacks around the Vulkan ecosystem, but using OpenCL as the original reference implementation. Many people would claim that CUDA is much faster than OpenCL, and that's true. But as I've shown you, there's like a one-to-one mapping between the functionality, well, in OpenCL and the basic functionality of CUDA. So you can actually generate CUDA binaries and CUDA source code from your original OpenCL code. It's much harder if you do it in the opposite direction. So every approach has its pros and cons. This one has some obvious ones. You have the same binary that runs everywhere. You have concurrent queues with Vulkan. So many years ago when I was just starting doing this, you had to use OpenCL and more outdated APIs. The problem with those is that very often, being designed for graphics first, they have just one single queue that you can either append or wait for execution. And like having a single queue for everything is often a very limiting requirement. And another beautiful thing is that Vulkan allows you merging devices into SLI groups implicitly. So instead of manually writing some kind of management code that kind of merges GPUs together or balances the load between 2 GPUs, if they're connected with SLI bridge, and if they have the same architecture and the same design and the same generation, then probably your code will scale automatically. The problem is that you have separate code base for OpenCL code and for C++, and people often don't like it. It requires some code duplication, and the compilers are kind of early stage, so the only compiler that generates a SPIRV from OpenCL is currently designed and maintained by Google. It's called CLSPV, and you can find links to it in the GitHub repo. So the flexible solution is the one including Halide. You have this embedded DSL, which is basically a C++ library, and then Halide does all the magic for you. It will generate the binaries, and then you will build some kind of a scheduler or some boilerplate to deploy those binaries. So one important thing to note is that GPGPU World does a lot of just-in-time compilation, but it's not the way you're required to do your stuff. So you can pre-generate your binaries beforehand and then write some kind of a management code that basically schedules all the operations and chains them together. So this approach has one very serious problem, is that it's Turing incomplete. So you cannot describe all kinds of abstractions within the Turing language and the Turing metacompiler. The problem is that you cannot explicitly describe recursion or, let's say, while loops that do not deterministically specify the number of rounds of execution. And this is like a major limitation that kind of limits Halide in many cases to image processing. The cleanest solution of all is probably SyCL with C++ 20 or 23 with ranges and STL algorithms that are prepared for executors. But the problem is that the compilers are super early stage, even earlier than the Google's CLSPV compiler for generating SPIRV binaries from OpenCL. So if you want to try it. I would love to hear your feedback. But the ecosystem is extremely immature and probably it's too early to design products on top of it. So the simplest solution of all is actually using the higher level libraries that we talked about in the middle, namely Eigen, which is designed for CPU, but it has experimental support for CUDA, or Arrayfire, which is like the most popular GPGPU library that does just-in-time compilation internally that requires minimum amount of learning. It's basically as easy as calling homebrew on your Mac OS or like sudo apt install like on your Linux machine and basically opening up your favorite IDE and starting working. Like, it's super simple. The problem is that sometimes the kernel fusion can be much weaker than in systems like SyCL or Halide. But on the positive side, it's as easy as it gets. So here's the table that I've promised you in the very beginning. If you take just one thing from this talk, this is the table you should take with you. So I hope it made things a little easier for you to navigate, but obviously this table, it's not filled with yes and no's. It's filled with many different kinds of expressions, and it basically replicates the complexity that we have in the GPGPU ecosystem right now. So if you want to achieve maximum performance today, I would either choose Halide or combining OpenCL and SPIRV. Probably the best approach for all, the one that I'm actually using myself, is designing computational graphs and some boilerplate code for managing asynchronous computations on top of the Vulkan API, and then writing most of the stuff in Halide, generating binaries that you can later manage with this Vulkan glue code. But if you face a case when, for whatever reason, Halide is not producing the best implementation or it's not showing the best numbers that you want to get, in that specific case, I would rather write some piece of OpenCL and then compile it separately and then just use it the same way you use the binaries that were produced with Halide. And maybe sometime in the future, we'll get C++ with SyCL support, with ranges and GPGPU. And there are a couple of committee groups that are actually working on this stuff. And primarily they're supported by existing high-performance computing libraries and frameworks. NVIDIA does a lot of stuff, HPX does a lot of stuff, but it's still very early stage. Probably, if you are a little more advanced, there are some tips and tricks that you can employ. So for OpenCL, the tips and tricks basically boil down to the limitations and the weaknesses of the platform. OpenCL is extremely outdated. If you have dependencies and inclusions between OpenCL files, very often you may not be able to actually implicitly compile your code if it's split into multiple files. So you may want to read the file contents manually, concatenate the strings, and then pass it into the just-in-time compiler. And that was like a bug in NVIDIA's implementation of OpenCL that was limiting this kind of functionality for years. Another thing to note is that in high-performance compute, we always trade performance for accuracy. And you may use those specific instructions or specific functions that basically fuse multiple operations together or cut off some of the limitations in IEEE 754 standard for floating point operations. But it's not always safe. And the very important thing to note is that you don't want to create too many comment buffers. So if you have too many comment buffers, the queues and the OpenCL standard may have hard time basically allocating memory for them, and you will have huge bottlenecks. For CUDA, it's a little bit different. In CUDA, the ecosystem is super mature. So if your only platform is NVIDIA GPU, then use the CUDA ecosystem because it's extremely powerful. The best thing to exist in the CUDA ecosystem is the mixed precision math libraries. So many of the CUDA devices now have specialized cores that do specific operations much faster than the ALU. Namely, in neural networks, we often do matrix multiplications. And there are tens of cores on the modern GPU architectures that do matrix multiplications for 4x4 matrices with a floating point 16 accuracy, but the performance reaches 100 teraflops. It's about 12 times more than you get on a high-end Intel CPU, which costs maybe like $15,000. And the GPU will be 4 times cheaper. So the ecosystem is very broad and very complicated. Today we've briefly covered some of the layers. We've covered lazy evaluation, scheduling, languages, and some part of linear algebra. But if you want to, we can talk more about compilers and symbolic graphs later on. The stuff that I currently work on may be interesting to some of you. If you want to apply the stuff that you've currently learned, all the cool computations that we recently covered, all the cool techniques and the libraries, you may want to do the stuff that I do, actually making AI and scalable computations much cheaper and much more efficient. So I'm trying to push the boundaries of what's achievable today. And one of the things is actually having AI systems that can learn faster than ever. So this specific AI model learns how to control a set of muscles. So it can be useful for robotics if we want to build larger robots that can automate a ton of stuff. So it learns first with people and it learns with dinosaurs. It's cool, right? It's the same model. If you want to do something more meaningful for society or like for humanity, you can do cancer research. So a couple of years ago, the AI models that do computer vision surpassed the human level performance. So right now, you have higher chances of getting good cancer treatment if you first done computer vision part than if you went to radiologist directly. So nowadays, actually, the high-end radiologist will probably use computer vision models to find cancer on your scans. And then the last but not the least is the one that I don't have a slide for, so I was finishing up today. It's actually knowledge generation, knowledge acquisition, and management. That's the stuff that I primarily work on. So nowadays, language models that analyze primarily textual data have surpassed what's called the deepfakes level. So the moment in time when you can generate texts that are indistinguishable from the real text written by people. It's very scary, especially in terms of the media and news production, but it was all made possible by the AI revolution that we had recently. So the newest model of all is called GPT-2. It was produced by OpenAI, and it has about 780 million parameters. So basically, imagine a statistical model that has close to 1 billion numbers that it has to optimize in order to compute, let's say, the next word in the sentence for autocompletion. For comparison, the number of neurons in a cat's brain is smaller than this number. So we're still far from the number of neurons that we have in the human brain, and there is no direct one-to-one mapping and equivalence between human neurons and the weights that we have in neural networks, but it's still relevant to note. And there are some limitations that the current ecosystem has. And I'm working on my current system for 4 years, and I've experienced and worked with every single part of the ecosystem that you see on the slide. They all have very different problems, and the one that I'm currently facing is that we are currently moving from the paradigm that when we're producing very optimized logic to a paradigm when we have a simple code, but very powerful compilers. And to make this possible, we need simple languages that are easy to parse, easy to reason about, and we need meta compilers that are able to inject stuff into our code. The problem with C++ is that it's extremely hard to parse. It will probably take me 2 or 3 years to write a proper C++ front end. So I'm currently at a stage when I'm considering designing a new programming language, which I call C*, that will cut down some part of the boilerplate and will be much, much simpler, somewhat similar to the Lisp paradigm when you have just a few brackets to describe all of the syntaxes. And there are many goals that every ambitious project like this has. like having performance higher than in C or C++, which sounds totally impossible. But that's what people thought when C++ said that we're going to generate binaries that are faster than C. And it's possible because we have inlining, and we have lambdas instead of callbacks that we can pass directly into the final function. So the compiler can actually optimize the memory accesses. The same thing can be done with kernel fusion. But for kernel fusion, we need programs that are easy to analyze. Another thing is that I want to make it super simple. And I want to make it flexible like Halide. So nowadays, we have many languages that appear on top of the LLVM toolchain. And LLVM being so modular, it's super easy for us to design something new on top of it. But the problem is that most of the languages actually don't introduce anything new. They just merge and combine the concepts that already exist. That's why I really hate the idea of designing my own programming language as much as possible. But Halide actually introduced some really bright things. The idea that we can actually think about for loops in a different way. Having one for loop and then being able to transform a one-dimensional for loop into a nested for loops, or basically switch the order of for loops or the order of variables, is an amazing capability that we never had in programming languages before. So those new control flow structures and control flow keywords can actually be used in different specific use cases. That's why when you have a simple programming language, it's easy to make it extendable. So every person who has like his own specific workload or specific idea in terms of designing his own keywords for control flow may be able to add something new into the language or interpreter. So if you have any new ideas regarding languages, I will be happy to discuss it afterwards in the booth. We don't have too much time, so we'll probably stop somewhere here. You can find the talk on GitHub. The project that I'm currently working on is called Unum. The website is unum.xyz. So it's deeply scientific. I work on some discrete math problems related primarily to graph theory. And in probabilistic modeling, I work on primarily recurrent neural networks and graph neural networks. So I design networks that scale much better in large environments, so that I can process orders of magnitude more data than anybody else. And then the problem is, how do you implement it as cross-platform as possible so that all kinds of devices can talk to each other and basically train large neural networks together. And it's not just neural networks, it's all kinds of machine learning, including like graph processing and everything that comes to mind when you think about Google or PageRank. So you can easily find me on all social networks. My nickname is Ashot Vardanian, Ash Vardanian. Feel free to contact me if you have any questions, and you can ask them now. So that's the end.
Okay, this was great. Thank you so much, Ashot. We have time for just one question, unfortunately.
Okay, let's start with the front row, and maybe like if it's short, the third row as well. Who knows?
Okay, let's try.
Thank you. Can you please give a brief overview of what AMD has? It's like NVIDIA has CUDA, AMD.
Yeah.
What does it have?
That's a tricky question, because like whatever AMD has is somewhat in the early stage. As I understand the ecosystem right now, they're walking away from OpenCL and they're not going to support it very deeply. So the last few generations of OpenCL, like 2.1 and 2.2, they were not widely adopted. So this is just the simple C-based language that exists. There is a set of libraries that are currently being ported onto the AMD hardware. It's primarily done by the companies who work on SyCL, and SyCL has many implementations. Actually, SyCL is more like a paradigm than a specific implementation. So there's implementation by a company called SyCL, and there's implementation by a company called CodePlay. Both of those, they accelerate a huge part of GPGPU that's inside of some of the machine learning frameworks. So part of the OpenCV was optimized, and then also part of TensorFlow was ported and optimized for the AMD hardware. But the problem is that the frameworks that are currently used in, let's say, AI research and GPGPU in general, like TensorFlow and PyTorch, they have very experimental support for AMD hardware, so like everybody just uses CUDA. If you want to use something really amazing and custom, just write it yourself. Like, unfortunately, that's the state of the ecosystem right now.